Chapter 1.8.10.1 Hardening Guide, Authentication Mechanisms. Selecting the right authentication mechanism for securing your Kubernetes cluster is crucial. There are various built-in options, each with its own pros and cons. It's best to enable as few mechanisms as possible to streamline user management and prevent unauthorized access. Kubernetes does not have a user database. It pulls user info from the authentication system. For production clusters with multiple users, external sources like OIDC are recommended over internal mechanisms like client certificates and service account tokens. X.509 Client Certificate Authentication. Kubernetes uses X.509 Client Certificate Authentication for system components like the kubelet when communicating with the API server. While this can also be used for user authentication, there are limitations to consider for production use. Client certificates cannot be revoked individually, posing a security risk if compromised. To manage this, it is recommended to set short lifetimes for user authentication credentials. If a certificate needs to be invalidated, the certificate authority must be rekeyed, potentially impacting cluster availability. Client certificates created in the cluster are not permanently recorded, so all issued certificates should be kept on record. Private keys used for authentication cannot be password protected, increasing vulnerability. Additionally, client certificate authentication requires a direct connection from the client to the API server without TLS termination points, complicating network architectures. Group data is embedded in the client certificate's O value, meaning user group memberships cannot be changed for the certificate's lifetime. Static token file. Storing credentials in a static token file on Kubernetes control plane node disks is not recommended for production servers due to security risks. Credentials are stored in clear text, making them vulnerable to exposure. Changing credentials requires restarting the API server process, impacting availability. There is no mechanism for users to rotate their own credentials, requiring cluster administrators to manually distribute new tokens. Additionally, there is no lockout mechanism to prevent brute force attacks. Bootstrap tokens. Bootstrap tokens are primarily used for adding nodes to clusters, not for user authentication. This is because they have fixed group memberships that are not ideal for general use. Generating these tokens manually can result in weak tokens, susceptible to being guessed by attackers. Additionally, there is no lockout mechanism to prevent brute force attacks, making it easier for hackers to crack the token. Due to these reasons, it is not recommended to use Bootstrap tokens for authentication purposes. Service account secret tokens. In Kubernetes, service account secrets are being replaced with Token Request API tokens as the default option for workloads to authenticate to the API server. These secrets do not have an expiry and remain valid until the associated service account is deleted. They are visible to any cluster user who can read secrets in the namespace they are defined in, and service accounts cannot be easily added to arbitrary groups, complicating RBAC management. Token Request API tokens. The Token Request API is beneficial for creating short-lived credentials for service authentication, but not ideal for user authentication due to the lack of a revocation method. Distributing credentials securely to users can also be difficult. To mitigate risks, It is advised to implement a short lifespan for token request tokens when using them for service authentication to minimize the impact of compromised tokens. OpenID Connect Token Authentication. Kubernetes allows for external authentication services to be integrated through OpenID Connect, OIDC. Various software can be utilized for this integration, but it is crucial to implement hardening measures. This includes isolating OIDC authentication software from general workloads, being aware of limitations with certain Kubernetes-managed services, and ensuring that OIDC tokens have a short lifespan to minimize risks associated with compromised tokens. Webhook Token Authentication. Webhook token authentication allows for external authentication providers to be integrated into Kubernetes by contacting an authentication service for a decision over a webhook. The suitability of this mechanism depends on the software used for the authentication service, and there are Kubernetes-specific considerations to consider. Configuring webhook authentication requires access to control plane server file systems, which may not be possible with managed Kubernetes unless the provider allows it. Software installed for this access should be isolated from general workloads as it runs with high privileges. Authenticating proxy. One way to integrate external authentication systems into Kubernetes is by using an authenticating proxy. This involves setting specific header values in requests from the proxy to indicate the username and group memberships for authorization. It is crucial to use securely configured TLS between the proxy and Kubernetes API server to prevent interception or sniffing attacks. Additionally, precautions must be taken to prevent unauthorized access by securing the headers from tampering by potential attackers.